The script illustrates the problem of sensor aliasing. We're going to use a monochrome sensor and understand the relationship between the sampling and the sensor of the monochrome sensor and the sampling and the spatial frequency of the scene. So the first scene we've set up here is an optical image that's a high quality optical image that's a sweep frequency. And it's high contrast at the top, low contrast at the bottom. This graph shows the intensity, the illuminance at the sensor as a function of spatial position in microns. And you can see the sweep frequency here. Returning to the optical image, we now are going to simulate from the optical image to the sensor. We've set up a 2 micron pixel sensor, and we execute the sensor compute command and produce a sensor image. And it looks pretty good. When we plot the electrons as a function of spatial position, we see it tracks. So now we're going to simulate the consequence of resizing the pixels, undersample the pixels, and by setting the pixel size to 6 microns, which is too coarse to really handle to resolve the spatial frequency. And you can see that now when we run the analysis, we have a undersampled case and we have spatial aliasing, so that the high spatial frequencies are aliased back to lower spatial frequencies. If we protect the sensor by putting in a higher optics F number, we blur out the high spatial frequencies and the aliasing is removed. So you can see the high spatial frequencies don't make it through, whereas in the previous case they come through as low spatial frequencies, lower spatial frequencies than they were in the original image, and that's the aliasing. And here they've been protected from aliasing by putting in a blurrier lens, an F number of 12, diffraction limit, but F number of 12. What does aliasing look like for non-harmonic patterns, things that aren't like sweep frequencies? Well, that's shown in this next bit. We're going to go create a scene that's a slanted bar edge, which is another conventional target that we use for estimating aliasing. And you can see that for the edge it shows up as jaggies. The undersampling means that the edge that's actually smooth doesn't look smooth. When we protect from aliasing by putting in the F number 12 lens, it basically blurs out the edge so that the intensities across the line are different, are smoother, so that the blurrier lens protects from the jaggies.